cis form, if they're on opposite sides of the ring, the trans form. And there are permanent differences in physical and chemical properties among these stereoisomers. And by the way, I didn't go beyond 6 carbons, although there are 7-membered rings, 8-membered rings, even 20-membered rings. But basically, nothing new happens once you get past carbons in a ring, except that the ring gets more flexible. You never really do get to the practical point where bonds can rotate completely around them. So this business of cis and trans works for all cyclo compounds, no matter how big or small they are. Now, stereochemistry is tough. It's one of the more difficult concepts for many students to work with. It's not tough conceptually, but it's tough to work with in your mind so that you can solve problems with it and understand three-dimensional differences between molecules. So you really have to work at it. You have to get your brain factored into picturing the three-dimensional aspects. I gave you some definitions. Make sure we have those straight. So generically, isomers are compounds that have the same formula. But there are 2 gross categories of isomers: stereoisomers and structural isomers. In science, the structural isomerism is considered to be the most obvious and most significant type of difference between isomers. So if 2 compounds are structural isomers, they're always referred to that way, like 1-chlorobutane versus 2-chlorobutane. Those are structural isomers. There obviously also are 3-dimensional differences between those 2, but we don't call them stereoisomers. We say they're related as structural isomers. You only use the term stereoisomer to describe the relationship between 2 molecules if the 3-dimensional difference is the only difference. Everything is still bonded in the same general sequence. It's just that for some reason, the way these substituents point in space is permanently different for one versus the other stereoisomer. And the simplest example is a ring, where the inability of the ring to rotate, restricted rotation, creates the possibility for that permanent 3-dimensional difference. Even though everything is bonded to the same position, there's a frozen 3-dimensional arrangement. And that can occur because of a ring and also a double bond. You also don't have any rotation around a carbon-carbon double bond because of the pi bond that's locking them in place. So you can have cis and trans stereoisomers with alkenes also. So cyclic compounds and alkenes. So in the case of rings and double bonds, the restricted rotation is the sole cause of the stereoisomerism. Now, there is another category of stereoisomer that is not based on restricted rotation, but it's based on what's called a chiral center. Chiral center, for our purposes, will be a carbon with 4 different substituents. There actually are other kinds of atoms that can be chiral centers, but we're going to keep this simple just for carbon. And you know that carbon has 4 bonds to itself. To have 4 different substituents, it has to be an sp3 carbon. So not an sp2 carbon or an sp carbon. Not a double bond carbon or a triple bond carbon. Just a plain, common sp3 carbon, 4 single bonds attached. Now, how can this occur? Well, actually, very easily. You look at a molecule that you're already very familiar with, 2-chlorobutane. That has 1 carbon with 4 different substituents. Now be careful, what I mean by substituent is the whole package attached to the carbon that I think might be chiral. So a methyl group and an ethyl group are 2 different groups. Don't be fooled by the fact that the carbon is the same, directly bonded. It's the whole package. So between the chlorine and the hydrogen and the methyl and the ethyl, that's a carbon with 4 different groups attached to it. Sometimes you see these chiral centers, or chiral carbons, if you will, with an asterisk next to them. That's how they're traditionally identified in a drawing where you're trying to point them out. Now, there's supposed to be a 3-dimensional issue here. What is it? Well, to look at 3 dimensions on a carbon, you have to get a little bit artistic. There is a stereo drawing for a carbon that you will see or have seen in your book that looks like this. The 2 solid lines are in the plane of the board. The wedge is coming out at you, the dashed line is going away. So if I wanted to look at that particular carbon in 3 dimensions, I would have to put it in the center of one of these drawings. And then put the 4 substituents on here. And I just put them arbitrarily on the 4 bonds. Make sure you understand in your mind that that's still 2-chlorobutane. CH3, CHCl, CH2, CH3. It's just an adulterated picture where the focus is clearly on that chiral carbon. Now if I make a model of that, so there's a chlorine, a hydrogen. I use this green for the chlorine. And then there's a CH3. It takes a little bit of time to put these together. It's faster with the computer, but not quite as good a learning experience. And if you have models, this is the time to use them. If If you don't, there are some in the organic lab that you can borrow. Just see one of the, myself or one of the professors. Here's my CH3. Last substituent here. Okay, I'm going to shorten this by leaving off the 5 hydrogens on the CH2, CH3, because by seeing the 2 carbons, you know what that is. Okay, so with the methyl and the hydrogen in the plane of the board, the chlorine coming out at you, and the ethyl group going away. This model corresponds to that drawing. Now, the stereoisomer of this that we're about to talk about is actually the mirror image of this. I can draw by imagining that I'm looking at this 3-dimensional object in the mirror. So I'm going to create what I would see in the mirror if I held this up to the mirror like this. Okay, so there's the mirror image. Let me put that together here quickly. I'll leave off the hydrogens again. So again, the single black carbon is the CH3. 2 carbons, the CH2, CH3, so the methyl and the hydrogen are in the plane of the board, and the chlorine is coming out. So these are the 2 models of those 2 mirror images, and if I try to line them up, they never do. You can line up part of the molecule, but 2 of the substituents are always crossed. So these 2 have a permanently different 3-dimensional difference that isn't due to any restricted rotation. It's due to a fundamental lack of symmetry in the molecule, and a chiral carbon is, in your book, you'll see, is sometimes called an asymmetric carbon, which means it has no symmetry whatsoever. Molecules that are asymmetric, or in fact any objects that are asymmetric, have a mirror image that's different from the original. And the classical example is your right and left hands. In fact, the word chiral is from the Greek word for hand. You put your 2 hands up like mirror images. One is, barring minor, of course, anatomical differences that we all have, you understand that your left hand is your mirror image of your right hand, but they're not the same. They're permanently different. So, and that makes that behave differently in certain circumstances. For instance, if you shake hands with a person and they put their right hand out and you put your left hand out, that's a very different situation than two right hands. Or if you're putting on a pair of gloves, you put a right-handed glove by mistake on your left hand, it doesn't fit properly. So there is a consequence to this asymmetry, so that two mirror images can appear to be two different objects. Now, what it does require is that whatever is sensing or interacting with these two objects has to always also be asymmetric. So asymmetry knows asymmetry in something else, but something that's symmetric is totally blind to this difference. For instance, if you take a classical pair of mittens, the kind that you may have had as a child, unlike a glove, a mitten will fit equally well on either hand, because mittens have a symmetry to them. You don't notice it because it's not the way typically the mitten is folded, but a mitten simply is like a light bulb with a thumb in front of it. And there is we call a plane of symmetry. I've talked about this before, a sigma plane right through that mitten. So that mitten is totally blind to the difference between right and left hands. Now you know the difference because your brain and your vision are asymmetric. That's an evolved phenomenon from birth. Your brain doesn't start out being asymmetric. It happens at about 6 months as one hemisphere of the brain begins to have certain functions that the other hemisphere does not, linked to vision, so that your right and left eyes provide this stereo asymmetric vision that allows you to tell different motions. So this motion right here, if you're familiar with old-fashioned analog clocks, that to you is a counterclockwise motion. This to you is a clockwise motion. Up to the age of about 6 months, this and this look exactly the same. And children don't typically wear shoes until about 6 months or so, but if you give an infant a pair of shoes, they're totally capable of telling the right shoe from the left shoe. And it's not that they don't know left from right, they don't even see the difference. They look exactly the same, but they can't tell asymmetry like that. The brain is still operating symmetrically. Now, what does this have to do with chemistry? Well, molecules are really objects, and if you take one of these, 2-chlorobutanes, one of these mirror images, and put it in, let's say, hexane. Hexane is a symmetric molecule. The way that this isomer interacts with the hexane is exactly the same, because the hexane is like a mitten, and it can't tell the difference between the two. If you melt these, let's say they're solids, or take a boiling point, heating is a random symmetrical process. It's sometimes hard to tell what's symmetrical and what isn't, but things like heat is typically not asymmetric. So they have the same melting point, same boiling point, same solubility in symmetrical solvents. The only time the difference would show up is in what we call a chiral or asymmetric environment. Now, if that's so specialized, why talk about it? Well, it's not so specialized. Life is asymmetric. All of the chemistry that goes on in your body is, almost all of it, is asymmetric. You have proteins and nucleic acids and tons of small receptor molecules, all of which are like right or left-handed gloves, and can tell which of these two is coming at it. So if you want to talk about receptors on a cell surface, you could have a receptor that's chiral, and if 2-chlorobutane comes at it, you can see that that's different than that one mirror image is different from the other. Just the way a glove can tell whether this is your right hand or your left hand. And this provides very specific interaction. See, nature is really smart. This makes two molecules out of one. There are two different forms now for 2-chlorobutane, and they're going to have different interactions in a biological chemistry environment. Now, they have to have a way of distinguishing these two. First of all, how would you name the two? It has to be a stereo descriptor. The stereo descriptor, according to the IUPAC, is that one has a configuration labeled R, capital R, and the other a configuration labeled capital S. There's a set of rules for assigning R to one of them and S to the other. You have to follow the rules. IUPAC. Fundamentally, when you have an asymmetric carbon and you're assigning R and S, you have a particular configuration. That's called the absolute configuration. Your book will use that term. That's just a fancy term for it is what it is, wherever those four groups are. And you should realize that these are never going to easily interconvert. I would actually have to take two substituents off and reverse their positions to make one the same as the other. That's not going to happen easily or often. So in essence, if you have two different mirror image stereoisomers, that's permanent. So the absolute configuration at this carbon, which is the second carbon, is either 2R or 2S. The 2 identifies where the chiral carbon is in the base chain, because you may have more than one. So don't be confused by that. One will be 2R, 2-chlorobutane. And the other one simply will be 2S, 2-chlorobutane. The 2 gets repeated because there may be another chiral center somewhere else, in which case you could have 2R, 3S, 2-chloropentane or something like that if you have another asymmetric carbon. But let's just worry about this. How do you assign it? You're going to have to put numbers ultimately on each of those 4 different substituents. They're called priorities. 1, 2, 3, 4. The highest priority is 1. The lowest priority is 4. Now you have to go by the rules and stages. You look first at the 4 atoms that are directly attached to the asymmetric carbon. So I'm taking this one on the left here. This is the left-hand one. The CH3 I'm just drawing as a single carbon, and the CH2CH3 as a single carbon, because I'm only looking at the first set of 4 atoms directly bonded to the asymmetric carbon. Now, you use atomic number. Sounds like there could have been a better choice, but you use atomic number of the atoms to set the priorities. The one with the highest atomic number gets 1, the lowest atomic number gets 4, etc. So hydrogen, of course, is always 4 if it's one of the substituents. What would be number 1? Fluorine. Now I obviously have a tie. I don't know what's 2 and what's 3 because I have 2 carbons. What you do then, it's sort of like peeling an onion, is you take what you've already assigned and hold on to it. Once you assign a priority, stay with it. I'm just trying to decide which one of these is 2 and which one is 3. The carbons are useless for doing that, okay, because they're tied. Instead of going 1 bond out, go 2 bonds out to every atom that's attached 2 bonds away from the asymmetric carbon, because I had a wash at 1 bond. So this is a CH3, so that's 3 hydrogens. I'm going to add the atomic numbers of those 3 hydrogens up. 1 plus 1 plus 1, which of course is 3. Then here, I've got H, H, and another C. Yeah, I know. I'll get to it in a second. I do that all the time. Everybody see why that carbon appears on the far right there? I'm going 2 bonds away from the asymmetric carbon. And that's a hydrogen, and a carbon. The hydrogens that are way out on the end of the ethyl group haven't come into the picture yet. Again, it's like peeling an onion, just go 1 layer at a time. Now you can see the game is over because if you add up the 3 atoms on this side, remember it's atomic number, not atomic mass. That's 6 plus 1 plus 1, which is 8. Now, of course, you probably would have guessed that the ethyl group would beat the methyl group just by looking, but you can get fooled in a tricky example because it's just a set of rules. This is not science. This is just clerical work. How do you assign the configuration? And it's in your book just so that you kind of have an awareness of what it's about. If you have to do it, you will do it the way I do it, which is on a computer. Use a modeling program like the one I showed you. Draw the 3-dimensional picture of the particular configuration you want labeled and press a button, and either a capital R or a capital S will magically appear on that carbon. Now, is that cheating? Absolutely not, because assigning that R and S is not science. It's just busy work, okay? But you need to know how the system works, and your book gives you a lot of examples with it because it gets your brain looking at molecules in 3 dimensions. So it's more pedagogical than scientific, but still worth doing on simple examples. And I'll never give you anything more than a simple example. This can get nauseatingly complex with very complicated substituents, but it's just a set of rules, as long as you understand how it works. So, I'm going to reduce this to numbers. Let's see, this was 4, 1, so the ethyl group is the number 2, and the methyl group is the number 3. Okay, make sure you see that. I didn't chew before I fall over. So now you look at that, and there's another rule. Now that I've assigned the priorities supposedly correctly, there's another rule which is you have to look at this from a standard orientation. And the standard is number 4 has to be away from you. Let's see. This is the one here. So methyl, hydrogen, chlorine, ethyl. This is my number 4 substituent right here. I have to turn that so that I'm looking at the other 3 substituents, 1, 2, 3, coming out at me like this. So number 4 is my arm. Now why is that rule there? Because, is this clockwise or counterclockwise? Not to me. To me, it's clockwise. So what's the problem? Why do I see it as clockwise and you see it as counterclockwise? Well, who cares? The point is, we're going to get the wrong answer. One of us is going to be wrong. So what you have to do is fix that and say, you must always look at this clock from this direction. Not from the back side, but from the front side, and that's what that rule's about. If you look at it from the wrong perspective, you're going to say this is counterclockwise, when in fact it's clockwise according to the rules. So the rules would assign that as R, because R is the first letter of the Latin word that refers to right or clockwise. S is counterclockwise. Actually, S for sinister, which in Latin means left-handed. You may not be aware, but left-handed people used to be thought of as cursed. They had some kind of strange curse on them. Many, many years ago.
The one that you drew on the left, you only counted 6 plus 1 plus 1. You didn't count the 3 hydrogens that would be attached to that carbon.
Right, because they're 3 bonds away.
Okay, so you only counted the second one.
I was only at the 2 bond stage. Everything that's further than 2 bonds away is invisible, not counted, not there.
So you said that the 4th one has to be away from me fully?
Yes. Right. Now, it may not be that way in the drawing, and you can see that it's not in the drawing. That's the problem. So what the books will tell you to do is one of 2 things. Either move the molecule so that number 4 goes behind the paper or the board, or move what they call your mind's eye to a view that looks into this cone right here coming out. So the saying, look into